Beyond independence, advances in network inference by Gaussian graphical models. Over to you.
Thank you. Okay. Thank you, Magnus, for the introduction. So, as we were saying, we will talk about network inference in the context of biological application, of course. And the models that we will talk about are Gaussian graphical models. And in particular, we will focus on multimodal data. So this work is in collaboration with Bailey Andrew, that is here, and they will deliver later the tutorial. And Professor David Wested, this is the other co-supervisor of Bailey, that is in his final year of PhD. And yeah, let's get started. So the sections of the talk are as follows. So last year we gave a talk on the first version of our methodology. It's called GMGM. So we will start with a recap on Gaussian graphical models and this methodology that is a fast multi-axis Gaussian graphical model. Then we have the new parts that are the non-central GMGM and the strong product model. So we deal with some aspects of the model that we improved, that we embedded some extra, let's say, modeling, and then we have a little bit of discussion in general on the models. And finally, we will have all in practical. So we will have a demo, and you can run through examples with Bailey. So let's start with the background. So yeah, so sorry for the effect. I just I couldn't resist this GIF. So just to set the expectations, so the kind of network we will deal with are biological networks, I was saying. So we will try to model all sorts of interactions between nodes, and nodes can be cells, can be genes, can be molecules. So you can imagine these kind of settings or in all your kind of different application fields. Now, the Gaussian graphical models are a special case of undirected graphical model. So what is it? So you can imagine to have a multivariate random vector where there's a specified distribution on, and the components of that vector will be the nodes of the graph. And then with different approaches, you can just take the data and try to estimate the interactions between those. Now, in this case, we have undirected, meaning that there's no meaning in a direction from x1 to x2 or x2 to x1, for example. And the edges can be then summarized in terms of the adjacency matrix. It can be 0, 1, or different value instead of ones, if it is weighted. This is just general background. Now, as I was saying, not only this is a special kind of undirected graphical network, but it is a special kind, the GMGM, of conditional independence graph. So before looking at conditional independence graph, let's clarify what we mean by conditional independence. So imagine that in this toy graph, we want to identify two groups of nodes, A and B, that are completely isolated, separated by another set of nodes. Let's call it C. Now, there's different way we can do it here in this graph, but you can imagine that this can be A, x1, x2, and x3. This can be B, x5, and C is x4. So you can see that all the paths that will connect the nodes in A to the nodes in B will go through C. So that is your separating set. So this means that we have the global Markov property. That means that the vector in A is conditionally independent from the vector in B given C. Now, what we will actually look at in our modeling is the pairwise conditional independence. That means the conditional independence of two nodes given all the others. Okay, there's different Markov properties. This is the one we will consider because GMGM, finally we will understand what they are special cases of this conditional independence graph where the vertices are distributed as a multivariate normal, and then the weights are defined based on a precision matrix. That is the inverse of the covariance matrix. So we all model, we know that we need to specify the multivariate normal with the vector of the means and the matrix of covariances. Here we focus on the inverse. And there's a reason why we do so. The reason is that it embeds the partial, it's related to the partial correlation, and it embeds the conditional, encodes the conditional independent structure. That means that it can be shown that for each two nodes, I and j, the conditional independent given all the others, if and only if the partial correlation is 0. Okay, so we like this property. So we know that if we compute that inverse, all the 0 will correspond to conditional independence. And the sparsity pattern, so of that precision matrix, will express this relationship. So the fact that we study the G and Gn is that is linked to the fact that we want to study this conditional independence. It means we want to identify these zeros. So far, so clear? In any questions, just interrupt me. Okay, so that's what we want to estimate. Now, why, again, we want to do that rather than studying the correlation? So let's give an example in terms of genes. You can imagine to have 3 genes, very, very simple example that actually was used in this paper that I cited here. So you have 3 genes, 1, 2, and 3, and let's indicate their expression with x1, x2, and x3, and those are random IID vector 0, normal 0, 1. So you can imagine that the expression level of gene 1 is specified by a constant plus some random variation, and then gene 1 is positively regulating gene 2 here, and then it is negatively regulating gene 3, like this, okay? So we have a constant value plus positive regulation, negative regulation. Imagine we want to compute the correlation and the partial correlation matrix. When we compute the correlation will pick up on the dependency between x2 and x3 that is actually being created by x1, okay? But if we then compute the partial correlation matrix, what will happen is that that dependency disappears because the partial correlation only will highlight the direct dependencies rather than indirect dependency. So it's like we're conditioning out that dependency, and we can actually see that there's a 0 there. So this is a kind of magic property of this precision matrix or partial correlation matrix, because just a transformation will give you the relation between both. And it is what we want to focus on. So that's the kind of problem we're studying. And we like that this is sparse, because the kind of problems we will be dealing with, we have the assumption that they have a sparse precision matrix. So the dependency is expressed by a sparse matrix. And is this a valid assumption in biology in general? Well, for gene expression, because we were starting from that example, this is from this paper on Gaussian and mixed graphical models as multi-omic data analysis tool. And we have the case of single-cell RNA sequencing data from melanoma metastasis. And then we have the gene-gene correlation networks values and the gene partial correlation values. So as you can see, this gene-gene correlation is much more dense. Now, that means that practically all the genes are connected to each other, right? So that makes the correlation a bad measure of dependency, because I won't discover much. I just see that everything is connected to everything, right? But if I look at the partial correlations, I see that the range is practically the same because we go from -1 to 1, there we're going from -0.4 to 1, but it's much more narrow and it's much, much sparser. Now, the other main difference that I can just speak on is the fact that vanishing correlation is a good indication. It suggests independence. However, a high correlation is not a strong indicator of dependency. The other way around, a high partial correlation is a strong indicator of dependency. Okay, so that's the property we want to exploit. Yeah.
Is the theta ij, is that the precision?
No, that is the partial correlation. So in practice, the theta, that one, that is the.
So it's the inverse of the covariance.
Yeah, so we have to go. I didn't show the steps. Of course, you can work out. You first have to compute the correlation. Then you compute the inverse of the correlation, and then you get theta. And then you compute the partial correlation. I would have just used theta.
Where it says correlation, is that theta? I think that's theta to the -1.
Yeah, sorry, wrong. It's a wrong. Simply, I didn't notice that. Apologize. This is the sigma. Sorry, I should have used a different symbol. Yeah, correct. Sorry, I will correct the slides. Thank you. Yeah. Sorry if it was confusing. Yeah, absolutely. Thanks. Okay, so clear here. And about sparsity, so I will clarify that we want to study GGMs, Gaussian Graphical Models, where the theta is sparse, where we mean the precision matrix. It is the inverse of the covariance. And then this means more conditional independence variables and fewer elements to estimate. Now, what is a sparsity assumption? That means in practice from a graph point of view that there's the property that the maximum degree is smaller than the dimension of the graph. And this is a reasonable assumption as we've seen in many contexts, for example, in gene interaction networks. Now, sparsity is in general a good assumption because there's this Betton sparsity principle from Tibshirani that actually focus on the fact that usually the important features in a large data set are not as many as we can imagine. So we're better off anyway assuming that the most relevant features are not in a large number, so that your problem is sparse. Okay. And this is also the assumption of graphical lasso. That is, there are many approaches to estimate the precision matrices, and the most famous is the graphical lasso, introduced in different ways from Hasti, Friedman, Tibshirani. And what they do, they compute the maximum likelihood associated to the problem, and they regulate, let's say, the sparsity through the penalization. So that's the lambda. Okay. So that's this L1 penalty for this estimation. Now, this is a very good approach, and it's been massively used, and it's very, let's say, it's also fast, but there's some limitation. So the main limitation is that it assumes independence between features and samples. That means in the example of the genes and cells, when I'm estimating the gene network, I'm assuming that the cells are independent. But that's not the case in this kind of application. So it's less likely that is the case. And the other limitation is that In many situations, particularly when now we have a large experiment with many cells, we want to characterize the gene network and also the cells network. We want to be able to find clusters of cells and genes. So with the graphical lasso, we can only proceed on one of the axes. So we choose the genes or we choose the cells. If we wanted to do both, we would just violate the assumption of before, because when I estimate the gene network, I'm assuming the cells are independent and the other way around. So it's a bit of, yes, we still can do it, but. So in order to overcome these limitations, we need to identify a general framework that will model this conditional independence relationship. It's an initial step, it's the conditional independence. So it's not independence, but conditional independence between features and data points together, so that I can actually end up with two networks estimations along the two axes, in this example, cells and genes. Okay, and there are such frameworks indeed. First work that we mention here is the bigraphical lasso from Kalaitis and Altri, where they exploited the Kronecker sum of the two precision matrices that you can interpret as the graph along the two axes. You can imagine this is along the genes, this is along the cells, and that translates into the Cartesian product of the graphs. Okay, so this is an example, but it's not from biology. This is just an image from a data set called COIL, where there's rotating images, and this is a rotating duck. And so you can imagine one axis is the frames, and the other axis is the pixels of the images. And this is also another kind of application you can have for these approaches. Now, so this is a step in the right direction, but there are actually limitation due to the way this was implemented, because it was storing the overall precision matrix, the big omega. So it was a lot. So the memory explodes in this case, and also it was able to handle like low 100 samples. So we worked on this, and we introduced another approach that would make it faster and memory efficient, but that's not the only, the main contribution of this other work is called scalable. No, well, the software is called scalable bigraphical lasso, but the title there is two ways, sparse network inference for count data. We introduced something that is called, how do we call it? I don't think non-paranormal distribution with the Kronecker sum structure. So we use the Kronecker sum structure, but we consider the fact that the data we work with, they're not always Gaussian. So there could be counts, for example, as it is in the single cell cases. So we replace the Gaussianity assumption with a weaker Gaussian cupola assumption. And we used something that was introduced by Liu and Altri in 2009 that is called the non-paranormal skeptic. It's a kind of transformation that you can do, and we embedded this in our model. So we could work with counts. Okay, that's the thing. Then there's been other approaches that worked on scalability. So one is Teralasso, one is Egg Lasso. For example, there's other. Those are the one that we compared to, and they have a better space and time complexity. However, they still can run on low thousands in a reasonable amount of time. So that is a big improvement, but it doesn't scale to millions of features. And the reason why it doesn't is that all the algorithms we mentioned so far are iterative, and the iteration is linked to the regularization. And for each step, there's an eigen decomposition. That means we have O n to the power of 3 runtime. And actually the memory usage is optimal. We can do much less than that because that's the data. So there's still work to do because of this part, the runtime. Now, do we need to scale to millions of samples? Yes, because in the single cells experiments, we do have millions of cells. So yes, it is relevant to be able to do so. And also you can imagine you can have more complex experiments where you have different sources of data. And I will give you examples later. So what is the improvement we did in GMGM? Our approach that I will talk about in the second part of the talk like now. So we decided to remove this regularization and we use thresholding instead. So there's still an iterative part. So in practice, there is the eigenvector the decomposition, and then we iterate over the eigenvalues. And that was just in one slide, the main idea of this work. And now I will give more details about this approach. Again, Bailey has created the associated code, is here on GitHub, and we will play with, sorry.
Yeah, I have a couple questions. So
Yeah, go
you
ahead.
mentioned n square and p square, but wasn't the matrix sparse? So why is it n square and p square? For memory complexity and
Yeah,
time.
you don't know in advance how sparse it is. So you will, that's the idea we work on, let's say when we do the thresholding. I mean, that's the idea we work on later in the development of this methodology. Not the threshold, we do work on that aspect, and I will show you how. But in practice, you can assume it is sparse, but you can't really embed it at first. What did you say?
When that n squared plus b squared, when that statistic was cited, that was about prior work.
Yeah.
So that was the first implementation of this. And so we didn't build in sparse, like they assumed sparsity, but they didn't take advantage of that in terms of how they wrote the algorithm for complexity. So you're right, and as Luisa said, when later on you'll see that.
We will see that we will take that.
Better constant, not as constant, but better AC product.
Yeah. And another question is, why do you need the eigenvalue decomposition here? Just
Because you need so. We go back to the model. I don't know where I put the model. I guess we put it here. So we can imagine here, when we want to estimate these, okay, those are, there is a, so we don't invert directly the covariance, but in practice, we have to estimate the inverse of the covariance. So what we do that through a decomposition. Yeah, you cannot.
Yeah, when you write the optimizer to do it in your gradient, you'll find you need to take the inverse of this giant matrix, which will be like if you have 1 million cells and 20,000 genes, that's 1 million squared times 20,000 squared. So it's ridiculously large matrix. You never want to invert that. But
do you actually need the inverse or just turn it into phase? Or?
Yeah, exactly. So you don't need the inverse, and what you really need, you can get by looking at bits of ion decomposition, which have a special structure as well that you can take advantage of. So you don't need to have that giant computation in there. So all prior work basically has an ion decomposition that is somewhere in the algorithm based on the idea of avoiding inverting this ridiculous monster matrix.
Yeah, but you end up working in blocks anyway. So, but it comes from these parts because you still have to estimate, and then it's important to know that every time there's one here, there are two together. Okay. All doubts clear? Yeah. Great. So, yeah. Okay, so let's give more context to this GMGM. So we say it's a fast multi-axis Gaussian graphical model because not only we have this thresholding, but also we are able to work on multiple omics in this case. Okay, so multiple modalities, as long as they share one axis. And how do we do that? I'll show you in the next slides, but in practice, just for context, the reasoning behind this is that the examples we've seen so far was like one of the two. Okay, you have two axes, or you have this, or you have this. Imagine that you get given another data set where there's the measurements on the same axis as the other data set. Okay, in this case, it's people. Those are the same people. So you have people, species for the metagenomics, and people, metabolites for the metabolomics. So if you separate these two problems and you apply any of the methodologies we've been talking about so far, you will end up with different graph for the people. But actually, those are the same people. So you want a model that estimates those graphs, people, species, and metabolites at the same time in the same model. And that's what we do. And now we do that, we use this Kronecker sum normal distribution for each one of the modalities, and we use the same parameterization for the same axis, for the shared axis. Okay? That's the idea. And that's the answer to the question that you were asking before. So there are still some limitations. So the initial Eigen decomposition, as we were saying, costs a lot. So we can assume that both input dataset and precision matrices are low rank. So we can expect that the precision matrix is a low rank matrix. So we can have a guess on what that can be based on the variability in the data, okay? And we can use that. So we can actually not estimate everything, but just consider a fixed number of principal component, or if you want, eigenvectors, okay? So this is an example of the runtime. Those were TeraLasso, ELLIS, GMGM that we discussed so far. And then if we say, okay, we don't want to keep all the principal components, we just cut to 50 principal components, this is the runtime. Of course, this is like a wild cut because we just for the sake of making this plot, but there are reasonings you can do about the number of those principal components. And also, the other question could be, yeah, you do this approximation, but are you losing in terms of estimation? How do we do in terms of estimations? Are we good enough? So this is an example where we just give a rule of the thumb suggestion. So if you have a small data set, top example, this is a precision recall plot. What we have in blue is GMGM without cutting on the principal components. And then we have what happens in terms of precision recall when you consider 125 principal components or 60 principal components, and then we have the comparison with TeraLasso. So on the right, you have the explained variance. Okay, so you can see that for GMGM and TeraLasso, we have retained all the variants because, yeah?
Yeah, how do you compute a low rank approximation without with the eigenvalue?
We do. So we do a first step and we just keep the number of eigenvectors that we have decided.
You only want the top 10 eigenvectors. You don't have to do the whole item decomposition. You can just grab the top 10. So
Is there a method for that?
what's
Use some like Arnold
accessible and standard
With that.
packages. So you just do that. So you come up with a guess at first how many you need. You run it with that. You can then look at, for example, explain variance to see whether you feel like your guess of 50 principal components is reasonable for the data, and then adjust from there.
That iterative algorithm that doesn't like lose the sparsity of the matrix, that can take advantage of the sparsity.
Yes, yes. So at least in our implementation, we use SciPy's accessors to that, and they take advantage of sparsity. So, but if it's sparse matrix, it looks nicely.
But you only, so the advantage is you only have to do it in one step, so just once.
Yeah.
While when there was the penalty, you had to iterate. Okay, so, and that's just to answer your question before, that's the variability, you see? So the explained variance in the data with those components is given there. So you can see that even if we're not losing much, for example, with 60 or 125, the components, the corresponding precision recall curves are mostly affected. But this is because this is a small data set. You really don't need to do that for a small data set. You can just run any of the previous methodologies. And we suggest GMGM, of course, but that is not a problem runtime with that dimension. Just to give an idea of the effect that you have when you start cutting on and considering the sparsity based on the principal components. Here we have the variability associated with 500 principal components. So it's like really being hit, but still you do not have much loss in terms of precision recall. And then with 125 principal components, you of course is worse, but you can decide based on this more or less what is your cut. Yeah.
Problem gets larger, we also need more, like, to increase the rank of the approximation unit or more principal components. Like how do they scale together as the problem gets bigger and bigger?
I think it will depend on the data. It would depend.
I found that often for single cell data sets, I never need more than 100, even for very large ones, to get a graph that looks like, at least visually, like it's doing something interesting. But it will depend on the data. It could be that you're looking at something very complex and you need to take more.
Yeah.
Or maybe it's a very simple data set and you just want cell type in it, and then you need even less. It all depends.
So let's say on simulated data, because those are simulated from Barabasi-Albert graph, you can just have an idea of what happens in terms of this kind of behavior. So you might run a simulation study ahead of time if you have an idea of how your data should look like, and then you can have, okay. And then from there on, you don't have to discuss that anymore. So, for example, could be, yeah.
Another question. So these methods all have to do with linear dependencies. Are there any methods at all that deal with nonlinear dependencies between the genes, or is that usually not considered? Like linear correlation. So if you have like some nonlinear relationship, it would seem like there's no linear correlation, so there might actually be some relationship. So is there any literature on nonlinearity?
So two things. So to answer your question, yes, and I'll get into that in a second. But because we're looking at, we focus on non-paranormal skeptic. So yeah, I guess if you're looking at correlations, just pure correlation with Gaussian, then it's linear. I don't know how partial correlations, I don't actually know if those are linear for Gaussian data, but with the non-paranormal skeptic, actually, the relationship between Pearson correlation and like Kendall's tau and things like that is kind of by doing some type of non-paranormal skeptic. Like by applying that pre-processing, you're already not talking about a linear relationship. But even with all that said, yeah, so we're making a Gaussian calculus assumption. Let's say you didn't want to do that, you wanted to look at something more broadly. Our methods to just get your conditional dependencies non-parametrically. but I don't think there are any that don't make the independence assumption. I could be wrong on that.
So,
And
Mm.
yeah.
so in practice, we're not covering that. We went broadly with the copula, right? But still, there are assumptions because the data has to behave Gaussianly. So you keep some of the properties. So we didn't explore that, and yeah, could be next steps. But
I'll briefly add on that. Actually, when you do the non-thermal step, that the pre-processing step, I think it is computing the it's not Pearson, it's not Kendall, it's that Spearman.
Spearman, right,
It's
yeah,
computing Spearman's row, and that's going into it. So there's your non-linearity there.
so yeah. Yeah, I do not have a precise answer though. So because we didn't explore it. So great, a great question. Thank you. And then part 2 of this talk is the new part, non-central GMGM. Again, there's the code on the GitHub repository from Bailey. So what is the problem with uncentered data? What we didn't focus on so far is that all the models we've been talking about assume that the data are centered. That means they got 0 mean. But particularly in the case of multi-axis data sets, the inference is done in a one sample scenario because let's say we give up the independence assumption, so we do not have repetition. It's like the observation is the only observation that we got of the data. It's like we have one sample. So estimating the global mean and removing it from the data can cause problems. Let's say it's wrong. So how do we relax the 0 mean assumption? Very intuitively, because we use a Kronecker sum structure on the precision matrices, we can use as well a Kronecker sum structure on the means. Okay. And this can be solved efficiently embedded in the likelihood, and we use the same kind of approach with coordinate descent. And we find that this is an improvement in the model. Of course, it adds computational time because then at this point, you have then to estimate the precision matrix, estimate the means, and then go back until convergence, like flipping between the two. So it adds computational time, but those are the results that makes it think that it's worth it. So we generated data that are not not centered, not without 0 mean. So this is a Barabasi algorithm graph with 100 nodes. And here we applied GMGM with no correction at all. And of course, the precision recall curve is terrible. Same thing happens with the projected GMGM, the means. We just have one step of this estimation of the mean. So we estimate the mean once. But then as soon as we start this iteration, estimating the mean, the precision matrix, and just have 2 steps, this is how the precision recall curve looks. So it's a big improvement. And this is how it looks at convergence. So this proves that actually it is needed when your data are not centered. So moreover, so what we did with this non-centered approach, yeah?
Why center the data?
Pardon me?
Why not just center the data?
That's what we said. So you can center the data. So you can imagine that it's more valid to center the data when you got samples to estimate from and you center the data. But in a scenario like this, you have like one sample because we're removing the independence assumption. So you can imagine we do not have replicates.
With one sample, can you even estimate with any precision the mean?
Yep, that's well, I'll talk about this in a second. But in practice, what we do, that's why we impose a structure that relates the precision matrices so that we get the better estimation.
So, yeah, you're right with one sample, like, so let's say you have a matrix, and you just have one sample of that matrix, and when you find the mean, of all elements, like each element has one mean, obviously, you're not gonna be able to do that with no precision, at all. But you can say, what if the mean has a special structure, because maybe there's row means and column means that are interacting, maybe you add the row mean and column mean to get the mean at that point. Now that's something you can.
Increase the sample size, basically.
It's more that you've reduced your parameter space, but
yeah, because if you don't impose a structure, your parameter space is really large. But with imposing your structure, you reduce it drastically, let's say. So, as a remark, this approach is not self-standing, let's say, it's a wrapper. So you can use any other methodology that is estimating a precision matrix, and you can just plug it in this wrapper, okay? So this non-central GEM is a drop-in wrapper for pre-existing methods. And of course, you might wonder about convergence. So in the paper, we show that there is a global maximum. This is a global maximum likelihood estimator that we get. So, and this is another example of applying R correction to the coil dataset where there was the rotating duct. So you can imagine that if you want to link all the frames of the duct that is rotating, because the duct is rotating, those are linked one to another. So you should have a circle there. If you don't center the data, you don't recover all the connections. So there are empty, let's say, parts here. There's no connection between some of the frames. And there is also a not tidy, let's say, estimation. So there are connections where actually there should not be there. But when you do correct with our non-central approach, both with GM or using or using our methodology as a wrapper, we get a better estimation. You can just say see it visually. Yeah.
In practice, is there an application for when you need to estimate the need from a single data point? Like, is there an application where you only have this one point?
Yes. In the multi-axis example that we are given, it is, so this, go back to this. Sorry. This is an example because I'm removing the independence assumption. So this is one sample.
Conceptually, we view the whole data set as a single sample.
Yeah.
Because we're parameters and everything to the data set.
So don't get snapshots of that same data set? No?
I guess if you had a scenario where you were doing longitudinal, or like you had, then yeah, you get multiple samples. Although in our approach, then we would add that as another axis, maybe, and look at the dependencies from that.
You only really get mean because with data you assume it's IID.
Yeah.
You get a load of IID samples. But in practice, they're usually not IID names with just one stuff.
Yeah, it's because if you don't get that in your assumption, then you lose it, and then that is your observation, and it's one observation that, and now I will explain. I will go in a more philosophical, let's say, part of the talk with this last part. Then maybe we clarify some of these questions, so we'll give you more answer, I guess. Yeah. So the strong product model came out from this kind of reasoning from Bailey, and also for this, there's a GitHub repository for the implementation. So this is a new model for the estimation of the precision matrices. And let's see which are our assumptions. So just to give more context and to this kind of philosophical discussion, so let's stick to the example that we kept from the beginning of cells and genes, okay? So we've seen so far that we estimate the dependency between cells and the dependency with between genes with this conditional independence. And we have used Kronecker sum. But what kind of dependencies between genes are we actually modeling? So let's look at this example where we have, imagine those two colors are two different cells, and we have 3 genes there, X, Y, and Z. So consider the situation where X is influencing, it's relating somehow, the expression of X affects the expression of Y when they are in the same cell, but it doesn't affect the expression of Y when it is in another cell. This other situation is where Z, the expression of Z affects the expression of X when it's in another cell, but it's not affecting the expression of X in the same cell. So those are two different ways of interacting of genes that you might find motivations biologically. So that are within cell and between cell interaction. So with our approach of the Kronecker sum, we are actually modeling the within cell dependency, but we're not modeling the between cell. And you can think of within row or between row in this case. So as we were saying, you got your single sample with all those parameters. We can impose to solve this problem a specific, let's say, structure that relates rows and columns, like the precision matrix along the row and rows and the precision matrix along the columns. So what we have used in our GMGM, there is the Kronecker sum that will express the within row dependency. And it translates into the Cartesian product of graph as a graph operation. That's the relationship there. Or another product is the Kronecker product that will express the between row dependency. And this translates into the tensor product. So a way of putting those together very intuitively is just summing them up, right? And this will give us the strong product model that is actually, from a graph operation point of view, is the strong product of graphs. But how do we add this together? So this precision matrix and this precision matrix are actually different because one is expressing the between row. Sorry, am I doing it? No, it's the other one, between row. And the other one is the within rows. So if I use the cells and I keep the same precision matrix for the cell, and I use the genes within cells and genes between cells precision matrix in this sum, that's our model. This is the strong product. That's what we did. So there's two parts, but we keeping the same, let's say, the same precision matrix along the same axis in the two parts. And we are splitting, let's say, this variability into these two. Okay. Yeah, I think it's this way, it's the columns. Well, it doesn't matter, it's a matter of calling them. Yeah. So it depends what you call in columns and rows, but in practice, that is it. Okay, so in terms of results, we simulated some data with this model where A, B, and C are Barabasi-Albert random graphs with 500 nodes each. What you can see from the precision reports along the rows and along the columns for the within rows variability and the between rows variability, and you compare the different models that are strong product, GMGM, Kronecker sum, that means what we mean there for Kronecker sum and Kronecker product are these two parts, if you consider only this, or if you consider only this. Okay. So the two parts separated from the same model from our implementation. So in practice, overall, the strong product does pretty well because it's the one that puts together the Kronecker sum and Kronecker product results in our implementation with our algorithm. So we kind of powering up those two. So we are doing pretty well there. But comparably with other approaches, that in this case is the GMGM, but we are the only one that estimates in one go, so 3 graphs that are the one for the dependencies of the rows and the one that expressed within row and between row dependencies. Okay, so in practice we have in one run a graph for free because it comes with the estimation, and we have a good recovery. That's the, let's say, the main point is that the strong product is the only one that learns both type of column graphs. Yeah.
What is the output of this method expected to be from a practitioner's point of view? Is it the groups of genes?
It's the graphs, and then, yeah, it's the graphs, and then you can study those graphs as you wish, because just just to stick to the example, in this case we will have the dependency between the cells, and then we will have the dependencies between genes in the same cells and genes in the dependency between, how do they interact between cells. That's your interpretation of the output. And then depending on what you want to study, you can just go off and study those graphs, those mechanisms. Of course, this must be heavily related to your biological question, because then validating these outputs, it is strongly linked to your biological question, and it is not easy because you need an expert to talk to, and I mean, if you are a computational person.
Is it fair to say that it's like for generated causal hypothesis or hypothesis for causal diagrams?
So there's no causality here yet. We were thinking of introducing the causality, but we have not. Yeah.
Yeah, that's a hypothesis for potential.
Yeah, it is yeah, you can just say this could be the starting point. I get your question now. Yeah, it could be the starting point for causality related questions, because you can start seeing something, you can just guess some mechanism who is doing what. Yeah. Great. And we are, I believe, at the last slide here, where we have an application to a single cell data set. We have a data set from Butner et al. In 2015. Those were labeled cell stages. We have 288 mouse embryonic stem cells, and we selected 167 genes related to the mitosis. So the cell cycle labels that we have on the cells are G1, S, and G2M. So with that in mind, we run our approach. So we have the precision matrix that express the cells dependencies, and then the 2 precision matrices that look at the genes dependencies. Now, because we have the labels of the cells, in order to account for validation, we use the graph along the cells, and we use as a measure the assortativity. The assortativity measures the tendencies of cells within the same stage, in this case, to connect, okay? It's a measure. And it is between -1 and 1. And 1 indicates that the cells in the same stage, in this case, tend to connect. -1 means that they tend not to connect. It means they actually tend to connect to the cells in the other stages. And 0, there's no tendency that you can find. It's a bit like correlation. Now, when we run strong product, we can see that within our assumption, that means sparsity, we reach the maximum assortativity, that is in this case about to 0.215 with a sparse graph. Okay. While in the case of GM, the maximum assortativity is reached after for a much less sparser or a more, let's say, a more dense graph. But our assumption is compatible with the result here, that is sparsity. So we know that there will be few relevant features, few let's say significant dependencies. So we expect that the most relevant interaction would be much smaller than the dimension of the graph. So we expect that dependency, a graph to be sparse. So we are in this case. So in that sense, we can interpret this as a win. Any questions related to this plot or in general? So what happens now is that this was the last slide of the talk. And I'm sorry, it was maybe a lot of talking about models and products and things like that. But there's going to be a much more fun part now, I hope so, that you will enjoy, with Bailey, Andrew, that put together a practical, and all that we've seen would be just through examples, and there would be interaction. So I leave this to Bailey.
Yeah, hello. All those plots that you see there, I'm not going to explain them because they're what you'll be creating in the practical. Hopefully you'll get an idea of how to run these algorithms and then what you actually do with the results once you have it. So wait, which computer is it? This computer or this one? Okay. I'll come back to that in a second. So the practical split into 3 parts, and I figured, well, we figured that we would have some time on each, and then you can kind of do your own work on it, and then maybe a brief I don't know what the word is, like coming back and discussing how you felt about it, and then if there are any questions, of course you can ask questions at any time. Yeah, so you may want to, before I click on it, if you have computers, try and go to that link. So it's just on GitHub, and then it's my name, Bailey Andrew, /ELLIS Summer School. And I will give like a minute to get there. And then I'll show you how to start it. You don't need to download the GitHub repository. We'll be able to do it online. Of course, you're welcome to if you want. But
if you have any questions in here, but you can have questions during the tutorial, of course. You have time to absorb all that I'll be talking about.
Yeah. Yeah, so I would recommend maybe if you can see it. I actually realize if you're way back over there, it may be hard to even see this link. But if you can, you should take a picture and I'll click on it. Anyone not at the link yet? Okay, I'll wait. I'll give a few more seconds. Okay. Unless someone shouts, I'm going to click the link. Oops. Oh yeah. Okay, that did work. Good. And you can see. How do I make that big? What?
I'm not busy.
Yes. Yeah. Just let's make. Okay. So when there should be a button here called code. You may have to fork the repository. If not, if you click code, you can go to code spaces. That's what we'll be. Is that button available for everyone? Yeah. Okay, good. I was worried we'd have to go through the process of forking the repository and all that. Great. So you go to code spaces, and just going to click this plus. I'll leave my cursor there for a second so that people can kind of see where to go. But if you're familiar with like Google Colab, GitHub Codespaces is very much like that. And so it will just create a version of this repository, but in the cloud. So you don't need to download anything on your computer. And if there's any problems, then let me know. It doesn't.
Have you logged in GitHub?
That's a good point. Yeah, you make sure you're logged into GitHub, otherwise it won't allow you to open Codespaces. And if you don't have GitHub, I guess you could just download the repository, but you probably should have GitHub. Yeah. So I'll go back to this in a second, but for those of you who have already created a Codespace, you'll see something pop up like this. There'll be two files that you need to be concerned with. So one is called, in all caps, setup. And that will be how you download all the packages you need. It's in notebooks, the folder notebooks. So you'll go to setup, and then just click run all. Oh, and if you have to choose a kernel, you want Python 3.12, which will show up at some point, I think. Because now everyone will be online. I think it's slower to connect.
They will run a little bit.
Yeah. Okay. So to reiterate, you click that green button, go to Codespaces, click plus. It'll open Codespaces, find the file called setup, and run it all. If it asks you to pick a kernel, you want Python 3.12. After that, you can go to tutorial and start it. Yeah, I'll come walking around, and it looks like Louise is too, so just flag us and we can help you.
Or because I saw the big something.
Yeah, so it might take some time. If you have got to running setup, just go to tutorial in all caps and you can start. But I'll leave it here for a bit in case people need to know where to go.